Okay, and we'll continue until we added everything together. So finally, this is a script that will be passing back to you. Of course, all the variable names are going to be randomized. They're just put this way for easier reading. And D1 is underlined because we're going to give you this whole new chunk of JavaScript and the variable name so that you know that that variable name in the end contains your shellcode string. The third one is JavaScript random text insertion. And what it does is it's also very commonly used in the wild. What we want to do here is the goal is not to beat AntiVirus. The goal is to simulate what's being used in the wild so that we can compare technologies. So this function call would ask us to ask Drivesploit to generate a random four character string and then insert into the original string for every 6 to 10 characters. And then we'll return you the new string. And number 4 is numeric literal mutation. A lot of times JavaScript AntiVirus is sampled by these fixed numeric literals. And so we'll have a function that's a slash space. So basically, you pass us a numeric literal or a hex code, and we would then randomly generate a computation that computes back to this hex code or byte, to this byte, right? So that your JavaScript, every time you serve to a new visitor, your JavaScript is going to look different every time. Well, that's basically what happens in the wild, so we want to simulate that. And so before, your JavaScript code would look like something like this, the line above. Now your JavaScript looks something like the line below. Okay. And then for the triggers, so we've covered Drivesploit for the first part, 5 features for mutation, and now for trigger prevention. So we want to know if we're in a sandbox environment, and if we do, and if we're not in a real human's browser, we don't want to execute. And this can be done a lot of times. You see that the trigger function is set on event handlers div unload and image unload. You see more image unload these days. Anybody want to guess which one is more effective? Div? Who think it's div? Who think it's image? Okay, a lot more people for image. Somebody say why? All right, come on. Why? Yes. The answer is yes. The answer is image unload is more effective, but why? It's yes. And the other reason is, the right answer is image load. Image unload is very effective for some of the newest and very accurate technologies, for example, ours. Div unload is very effective for older technologies that do not implement the DOM. Okay, so basically you take spikermonkey or rhino and use it as your JavaScript interpreter. These JavaScript interpreters don't have the DOM. Newer technologies like JS Unpack or VeriSign implements the DOM objects themselves, right? So if you're only using a JavaScript interpreter, because it's very hard to reuse IE. So typically we use some versions of Firefox, or just some versions of either spikermonkey or rhino, some versions of open source JavaScript interpreter. And div unload is very effective for that, for the older ones, because they don't have the DOM. They don't have DOM implementation. Image unload is effective for technologies that really sandbox IE and run IE as the detector. And the reason is because, IE has image unload, but what happens is when you're crawling millions of pages a day, this introduces a lot of bandwidth. And bandwidth and loading big images is just very, very costly. And so there's a feature in IE to disable image rendering, right? You click on Tools, Options, and you can disable image rendering. When you and some vendors do that, and when you disable that, image on load doesn't fire. Okay, so they pretty much figured out what these detectors are, what these detectors are doing to detect them. A third one is also very commonly used. It's just some do-while loop, some arbitrary do-while loop. But if you see here, what's here is in a do-while, there's an extra semicolon, which is actually a grammatic error. But IE is so smart that it can recover from that and continue, while spikermonkey or Firefox just throws an exception. So if you're using some versions of spikermonkey, it would throw an exception and then it wouldn't execute. While if you're a user using IE, and if I'm serving you an IE-based IE exploit, then it would work just fine. Oops. Sorry about that. Okay, so we implemented some of these, and then we tested it out. So we implemented these in Drivesploit, and then we generated the XML files, and then we uploaded them to VirusTotal, and we used IE peers as the JavaScript exploit. The plain IE peers on VirusTotal hit 17 detections. And randomizing variables, although it was pretty hard to do considering we had to parse JavaScript, wasn't really effective. So in Taiwanese, we call this bo cai. It means too bad for us. When we used random text injection into the shellcode itself, we brought this down to 13. So from 17 to 13, which is good. When we use random variables plus string shellcode string injection plus concatenation, meaning splitting it up, we ended up with 11 out of 42. So from 17 down to 11. So at this point, we pretty much thought that since we reduced 6 of them, we pretty much thought that roughly 6 of these antivirus detectors were based on the shellcode itself. Okay, so when we completely scrambled the shellcode, we only bypassed 6 of them, while the others was also sampling the rest part of the JavaScript, which included the memory corruption part and the heap spray part and the trigger part. And so when we used concatenation of shellcode plus the rest of the code, it came down to 1 out of 62, which was very good. Oh, which one? It's down here. It happens to be down here, so it happens to be down here. And this one, to be honest, is very good. Okay. And when we used injection of the shellcode plus concatenation of the rest of the code, just these two simple combinations were down to 0. And adding random vars, of course, the same. But VirusTotal uses versions that we use, which is the API version or the console version. But antivirus desktop versions is much stronger. Why? Because they can monitor host environment, they hook into browsers, so it's easier for them to get the raw form of exploit. If you hook into the browser, you can see exactly what the JavaScript engine is doing if you hook deep into the IE JavaScript engine, and as soon as you create a new variable with a raw form of shellcode, then I can say, boom, you're an exploit. So, And they can also do behavior analysis. For example, buffer overflow behavior or download to file behavior, which makes detection a lot easier. Okay, so this is the result of our limited testing of Drivesploit against these antivirus. We listed out, we abbreviated, you can guess. And we tried out the big ones. And as you can see, there was one vendor which Drivesploit could not beat. And as we use more features, for example, concatenation of the shellcode plus concatenation of the code itself, or injection of the shellcode plus concatenation of the code itself, we start to beat more and more antivirus. There was one vendor worth mentioning, and this vendor, as you can see, it has 2 scores because the static part wasn't that good, meaning that if we put all the HTML files that's generated and we asked to scan the folder, it couldn't find a lot of the exploits. But when we actually run the IE and have Metasploit served to us, then it's basically using its HIPS, host-based intrusion prevention system, it was able to detect every one of them doing buffer overflows. Okay. So we're originally going to do a demo to show you how, as we add more triggers, we can bypass, add more of these features, we can bypass most of them, but I think we're going to be out of time, and we'll leave time for some questions. So finally, again, this is to be triggering behavior-based encryption. When we turn on this feature and we submit to wepawet, for example, it doesn't find anything. And what happens is, if you change our eval into alert, and you alert it in Firefox, it doesn't show you anything. Okay? But you alert in IE, and it shows you the actual, what we're trying to do, the exploit. So what we did is we said, okay, we're going to encrypt our exploit with a key. And that piece of key can only be generated if you are the correct target browser. So if you're IE7, then if this exploit is for IE7, then only IE7 is going to be able to generate that key. So as you can see, every browser has a lot of different features and different behaviors. The rendering of CSS is very different from every minor versions of browsers. So we implemented a lot of checks based on CSS rendering, based on HTML parsing, based on JavaScript differences. All these, we put all these together, and we came up with a lot of checks. So you would say, okay, this exploit works only for IE6. Give me an encrypted version of my JavaScript exploit, and give me JavaScript to generate the decoding key. And the key is only correctly generated if JavaScript is run under IE6. So what we would do is we would say, okay, in order to correctly detect IE6, we're going to use this subset of our checks: 1, 3, 4, 6, 8, 9, 12, 14. All right, and we're going to generate, we're going to assign them to each variable. We're going to generate this piece of JavaScript to be served together with the exploit, and then we would generate the correct answers. If you are IE6, the correct answers should be those. And then we would scramble it up. So as you can see, the R value is scrambled up, but the L value, which is ABCDE, remains the same. And that effectively scrambles up the bits, the correct bits. Which means, although we're serving to a lot of IE6, we're generating a one-time key for every browser. So it's not like IE6 always has the same key, right? Because of this randomization. And so we'll use this as the one-time key, and we'll encrypt, and we'll use server-side script, which in case Metasploit is in Ruby, to encrypt the JavaScript using